Okay, hey guys, I'm going to do a very basic example of how to look at something and then draw moment and shear diagrams, um, because a lot of people have been having issues with this, have had to come to office hours. I think half the people or so this past week made appointments, or that saw me made appointments specifically to talk about how to draw moment and shear diagrams. So I'm going to go over those briefly with you. I'm just going to give you some basic tips. It's not going to be all-encompassing by any means, but I think that having a lot of you already know most of it. You just need like a little nudge to actually get started. Okay, so let's look at the case where we have a point load. I'll say that this load is some load 2p, and that this thing is right in the middle. So this is L over 2, L over 2. We'll call this A, B, C. The way I think about this is that I always... Okay, so I think most of you will be able to draw the reactions right away. Let's not use red. Red is the psychologically intimidating color. And blue doesn't show up very well next to black. Let's do green. I think a lot of you will be able to get your reactions right away. Your reactions are just P and P. Or let's draw this over here. Because if your load is located halfway between, then you get half the forces on each one. I don't think a lot of you have problems with that. The problem is probably drawing it. So let's start. Our axial is very simple. It's just 0, right? Like we have no axial forces. There's nothing that acts in the x direction. So everything is just shear moment. So let's look at our shear diagram. Okay, I at the risk of confusing you, I will saw some of you. Well, let's just say this is P, this is P. I always start from 0, and I let the arrows on the diagram drive my drawing. So for example, if I start at 0, I say, oh, at the very beginning, I have to go up by P. This P, the arrow of this P is pointed upwards. So I'll go up, I'll call this P. So I'll go up to P. And then I stop. Like there's no other arrows here. No arrows from A to B. This entire distance, there's nothing acting here. So I stay constant all halfway through. And then this 2p is pointed downwards. So I say, oh, okay, I have to go down by 2p. So I'll go down by 2p. And then I have nothing from B to C. Say, okay, so I just keep going. Just keep swimming. Just keep swimming. I hope you guys aren't too young. I'm not that much older than you. Hopefully all of you know where that comes from. But yes, 2p, it goes, so yeah, it just stays constant, and then it goes up by p. At the very end, like, oh, this arrow is driving my shear upwards. So I end at p. I end at 0. Remember that this is a very odd way of thinking about it, because you're usually, well, you normally say, well, I have to end at p, and I have to start at p, and I have to end at negative p. But really, if you pretend that you're starting at 0 and let the arrows guide you, then you'll get the diagrams very easily. And then now if we look at our moment diagram, if we remember that, let me use a different color. If we remember that our moment diagram, our moment is just the integral of our shear. So what does this mean? This means that the slope of our moment diagram is equal to our shear, right? This is what the fundamental theorem of calculus, I believe. This is your slope, right? Your slope of your moment diagram is your shear. So let's go over here. What does this mean? Our moment, or the slope of our moment, our shear is constant. So the slope of our moment diagram has to be constant. So our thing has to be linear. As you go down from W, as you go from shear to moment, you pick up a power. So here, this is a constant. This is x to the 0th power. This is x to the 1st power. And you just have a line. If we use the the downward positive convention, and when we just go down and we go up. All right, so you see this is positive, right? This is positive slope. And over here, all of a sudden we have an increasing, we have a negative slope. So our thing starts decreasing. And this should make sense. Where this thing crosses the axis, it doesn't actually equal 0 at either of these 2 points, but it crosses the axis. So where that crosses the axis, you have your minimum or your maximum. In this case, it's maximum. And then if you're asked to draw the deflected shape, it just comes out to... I meant to get black. Yeah, it just comes out to like this. All right, so that was pretty straightforward, I think. Pretty basic example. Your actual equations for this, because this is one line and this is a second line. This is one line and this is a second line. You cannot represent this with a single equation. You have to use a piecewise function. So what do I mean by that? I mean that your v of x equals two different things. It equals p or it equals negative p. And it equals p for x less than L over 2, and it equals negative p for x greater than L over 2. I think that is obvious here. Your m of x here, m of x is going to be interesting. Your m of x is equal to px, right, for x less than L over 2. And it's equal to negative 2p plus px for x greater than L over 2. Negative 2pl negative 2pl plus px for x greater than L over 2. I'm not going to go into how you get these equations. If you don't understand how to get these, please come see me. But you should just need to keep in mind that these are two different. It's a piecewise function. The next example I'm going to do is a distributed load. The distributed load is a little more interesting. So let's draw our free body diagram here. Okay, so our axial is 0, right? Our axial is 0, so we're not going to even worry about that. If these two things, they're going to be equal. Our AY and our BY are going to be equal, and they're going to be equal to, this is the length L. Our AY and our BY are going to be equal to WL over 2. And again, if that is not, if you do not understand this, I think most of you will be able to get here. But if you don't understand this, definitely stop by and see how we got our reactions. And like I did for the last example, I'm going to let the arrows drive my diagram. So I start off at 0, and I say, well, I have a reaction here. I start off at 0, but this reaction, this WL over 2, it drives my shear diagram upwards. I just follow the arrow. So this goes up to WL over 2. And then this thing here, this distributed load, it drives me downward. And I have to say, well, how far does it drive me down? It drives me down by W times L, right? Because if I go all the way down, I keep going down, 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 down. But then how far do I actually go? I go down by WL. So WL over 2 minus WL is equal to negative WL over 2. So I draw the beginning point and the end point, and then I draw a line connecting the two. And then I look at this and I say, well, now this reaction here is driving my shear diagram up again. It drives it up by WL over 2. And this is positive, this is negative, and all is good. Now note that this W is constant. W of x equals W, right? Like I can make W a function, but then because W of x is constant, I have no x term in here. Like what is W at L? W. What is W at L over 2? W. What is W at 0? It's W. So I can do that without any problems. But when I go to my shear goes up by 1 power. So I mentioned this earlier in the video, but if this is x to the 0th power, right? Because x to the 0th power equals 1. X to the 1 equals x. X squared equals x squared. So if this is really this is really x to the 0 power here. Well, I don't want it. I should use multiplication. W times x to the 0th power. Down here, my shear, it goes up by a power, right? Like I have a line here. I don't have a constant. I have a line that has a slope. So my V of x is WL over 2 minus WX. Right? I have an x term in here. This x is x to the 1. My moment term, my moment down here, I have the shear diagram is a slope of my moment diagram. My moment equation is on the order of x squared, because this was x to the 1, this was x to the 0. So this is x squared. And I say, oh, this diagram is very steep here. It's very steep and positive. So I draw a steep positive arrow. It's 0 somewhere down here. I know that it becomes 0, so I'll label this here. And it ends on a negative note. It has a very negative slope at the end. So I have that, and then I just like this. So you can see it's really not scary, I guess is the word. It really isn't. Your m of x is equal to I believe, and if you take the derivative of this, you get WL over 2 minus WX, and you have your moment is 0 at the beginning. So that is fine. Now let's go into a third case. Let's go into the case of a triangular load. And I know this video is going to be long, but you're only watching this if you need help, so it should be worthwhile. Well, let's go into the triangular load case. We'll call this A, we'll call this B, we'll call this L. We'll draw our free body diagram. This is 0. Okay, so you have all your things here. Your reactions So when you, so you see your reactions, you're gonna want to look at your thing here. This, your equation for W is now a function of x. It's no longer constant, right? Because this is a line. So this is, we want to find the slope of this line. So let's call this end, we'll call this P. Normally P is used for a point load, but if I call this W, then I'm going to get my W's and my Omegas mixed up. And you're going to hear me correcting myself like every 10 seconds. And that's not helpful for either of us. So I'm going to call this P over here. And the slope of this line is just P over L, right? Like it goes up by P over some distance L. So my rise is P, my run is L. And this is a function of x. And I start at 0, right? Y equals mx plus b. My b is my y-intercept. My y-intercept here, my intercept is 0. So this is 0. So my w of x equals p over lx. And I think that you'll see here that my x, this is x to the power of 1. Now let's look at the shear. The shear for this diagram, I will say that AY is equal to WL over 6 and BY is equal to WL over 3. I'm not going to say how I got those, but that's just for your reference. The important thing to note is that AY is 1/2 of BY. So when I come over here, I'm going to draw my shear diagram. I'm going to draw my shear diagram very carefully, and we're going to say like, oh look, I know that my shear diagram, it goes up by 1 power. It's going to be parabolic. There has to be an x squared term in here. Because it's x squared, that means I'm not going to have a linear term. My graph is not going to be a line. My graph is going to be a parabola. It's like, oh, I go up by WL over 6. And I end at WL over 3. Yeah, so I won't go into that now, but let's look at what is the slope here. The slope, the derivative of v should be your omega, negative omega. So this should give you an idea of what your slope is. Your slope here is 0. So we're going to draw your 0 slope here. Your slope over here is maximum. So that means that your slope here is it's maximum and it's positive. So it's positive here, and positive times a negative makes a negative. I think I'm going to lose some people here, but positive times a negative means you have a negative slope. So your slope is going to end like this. So your slope is just going to be like, the diagram for your shear diagram is just going to look like this. And at the very end, it goes up by WL over 3. So should be very. This part should be. I hope this is clear. Like this is parabolic. This last part was linear, and I went up by 1 power, and then I went from a line to the next power up. The next more complicated thing is quadratic. The next thing higher than that is a cubic function, and my moment is going to be cubic. So let's look. My moment is going to start off with some constant slope, right? And the slope is going to be it's going to start at 0, and it's going to be constant. It's not going to be constant. It's going to be increasing, and it's going to be a positive slope. It's going to be a large positive slope. Over here, it's going to end at a even steeper slope. It's going to be negative slope, but the slope is going to be very steep. It's going to be twice as steep as it is over here. So I drew my thing. I'm going to draw this a little bit shallow, and I'm going to draw this very steep. And then I'm going x2. So you'll notice that this, it doesn't line up perfectly. Remember that your 0 should occur here. So let me... wherever it crosses the axis is where you should have a minimum or a maximum. And now let's look at the graph. Does it make sense, or it should make sense, that where you have the higher load, you should have the larger moment? Because if you remember that your moment diagram looks like your deflection, but that also works in reverse. Your deflection should look, your diagram should look like, your moment diagram, how to say this, you normally get your diagram from how the moment, normally get your deformation from what the moment diagram looks like, but you can get your moment diagram from how your thing should look like when it's deflected. I don't have a good example right now, but if you put more weight here, for example, like I have this, right? And then if I put more weight here, do you guys see how this point is going further down? The minimum is closer to the right hand side than it is the left hand side. And that's the same thing you should expect here. You have a higher load here, so your maximum deflection should be located somewhere over here, or closer to B than it is to A. And you have that. You have that here. You have your 0 here, your minimum or your maximum here is closer to B than it is to A. And this is a cubic function. This is on the order of x to the third. So when you're drawing this, say cubic, say quadratic. It's important because we can't always tell. Like, the easiest way for us to grade this is to grade it based on the sign and on the power, and it's not always easy for us to tell. Anyway, I'm running out of battery here, so I'm going to hurry up and finish this, but let us know if you have any questions about this assignment or about anything related to the quiz. I'll probably post more in an email, so be on the lookout for that. Yeah, let us know if you have any questions.